students, good morning. Welcome to this video session. My name is Samuel Dominic Chukwuemeka, aka Sam Dom for Peace. In this video session, we shall continue our discussion on relations and functions. This is part 2 of the video playlist. This is a video playlist on relations and functions. So please, before you view this video, it is recommended that you have viewed the video playlist in order. Okay, view the video playlist in order. View part 1 before you view part 2. What we are going to be talking about, some of the things, if you want to write as I explain, that's fine. But the notes of what I am explaining are the link to the video playlist and other resources and the calculators is going to be on my website. You can get it on my website, www.samuelchukwuemeka.com or www.chukwuemekasamuel.com, or you can just go directly to this website, www.relations-functions.artspot.com. This will contain the explanations, the notes, the link to the videos, other resources, as well as the calculators. Alright, so in this video we shall talk about we shall give more examples of relations, functions. Then we are going to talk about 1-to-1 function, on-to function, and then the bijective function. So we have relation, we have function, we have 1-to-1 function. We have relation, we have function, we have 1-to-1 function. Under functions we have 1-to-1, 1-to-1 function, or what we call function, or what we call injective function. 1-to-1 or injective function. Injective function. Okay? Then we have onto function. Onto function. Onto function, otherwise known as surjective function. Surjective function. And then we have a bijective function. Bijective function. So a function must be a relation first. You cannot have something that is a function but not a relation. A function must be a relation. First and foremost, it must be a relation. So all functions are relations. However, not all relations are functions. Then A 1-to-1 function or an injective function must be a function first. It must be a 1-to-1 function must be a function first. Now, so we can say all 1-to-1 functions are functions, but not all functions are 1-to-1 functions. Okay? The same thing with onto. Now, we can't say onto must be a 1-to-1 first, no. So with these two guys here, okay, this onto function must be a function first. You can have something that is an onto function but not a function. It's not possible. So an onto function must be a function first. So we can say all onto functions are functions. However, not all functions are onto functions. Okay? So with 1-to-1 function and onto function, they must be functions first. And functions must be relations first. Okay? So if you want, I can kind of draw an arrow that this must be this first. Okay? And then this must be this first. And then this could be this could be this. Okay? Now for these two folks here, a bijective function must be 1-to-1 function and onto function. A bi means two. It's both of them. So it's both of them. These two gives you now bijective. This two now gives you bijective function. So we're going to explain these things and we're going to give examples of it. Now let us recall. We know that y is a function of x. In algebra, in calculus, we know that y is a function of x. Y is the dependent variable and x is the independent variable. We talked about this. We've talked about this in the first video. Relations and functions, introduction, domain and range. We talked about those. So y is the dependent. Y depends on x. Y is the dependent variable. X is the independent variable. Economics, bring it to economics. Y is the output. X is the input. For every input, you would have an output. Okay? X is the input, Y is the output. When you spend more hours to study, okay, your GPA will be the output. You have a good GPA. When you spend more hours to play video games, you have a bad GPA, right? Okay, please don't, I don't want to, I'm just giving examples, okay? So bring it to economics. X is the input, Y is the output. Bring it to statistics. X is the explanatory variable or predictor variable. And Y is the response variable. You use X to predict the Y. So X is the predictor variable, Y is the response variable in statistics. Or you can say X is the explanatory variable and Y is the response variable. Bring it to philosophy. Cause and effect. Cause-effect relationship. X is the cause, Y is the effect. So you can see like interdisciplinary terms with Y and X. Okay, so we define relation that for, like I said, what I'm explaining is here. The notes are all here. So don't expect me to write it because I have already written it here. Whatever I'm explaining, I've already written it here. So I want to just show you examples and make you to understand the concept. Okay, but for the notes, it's better you listen and see how I do it. And the notes are already here. But you can also write if you want to. Now, but when I'm solving something, you should not write. Okay. Now, so you can see the interdisciplinary terms related with this. Okay. So let's still on recall, backtrack to video 1. We define relation. Okay, relation. For every input, there is an output. Okay. For every input, there is an output. That is how we define relation. That for every input, you have an output. We talked about those. We talked about it in video 1. Okay. For relation, for every input, you have an output. I'm using input output because it makes more meaning. You know, some people will use for every independent variable, there is a dependent variable. I mean, that's the actual term we should be using. However, I'm using input output, which it doesn't matter. Okay, it doesn't matter at all because you can also input output relationship is still okay. Okay, so a relation is a set of ordered pairs for which there is every output for each input. Okay, for each input you have an output. Now, an input can have one output, an input can have two outputs. Input is the X, output is the Y. An input can have three outputs. An input can have 4 outputs. An input can have 10 outputs. The same input. Okay? The same input. That was how we define relation. For every input, there is an output. For each input, there is an output. There is at least an output. Let's define it that way. Okay? With a relation, for every input, there is at least an output. That is the correct term. That's because with a relation, an input can have one output, an input can have 2 outputs, an input can have 3 outputs, an input can have 4 outputs, an input can have 5 outputs. So with a relation is a set of ordered pairs in which there is at least an output for each input. Okay? There is at least an output for each input. Does that make sense? Now, you know, I was teaching this class. I'm not going to mention the place. So I was teaching this class at a college. So I asked students, can you give me an example of something that is not a relation at all? You know, sometimes when you spend so much effort studying. Have you ever thought about maybe you've spent so much time and effort on a particular course and at the end of the day, you did not pass the class? That ain't good, right? That ain't good, right? Well, it has an output, but the output is F. Okay, the output was F. Although that's not funny, I'm sorry. It's not funny at all. And I'm not laughing at you, no, I'm not. But, you know, sometimes you spend so much time and energy on a course and, you know, it doesn't make sense. You didn't pass the class, yeah. When all things fail, guess what? We look up to God. We say, God, please help me to pass this class. Please, Lord, help me to pass this class. No, there is nothing impossible with God. Nothing. So, because when you've spent so much time, so much energy, so much effort, reading, studying, staying up late at night, and yet you still flunk the class. See, that tells you it's not by your power. It's by the grace of God. It's just by the grace of God. Just by the grace of God. Simple. You know. So, in that case, there's an output anyway. But what I was saying is this. There was the joke I wanted to say. Well, I call it a joke, I don't know. But I was teaching, so I asked, can you guys give me any example of something that is not a relation, whereby you've spent, so, you know, there's input, but there is no output. And a student told me, a lady for that matter, so she said it was the example, the case was between her and her boyfriend, that she spent so much time to make it work, but the boy just messes up, you know. But that's by the way, you know, I'm not gonna deal with it, you know. So I said I don't know. So because, you know, when somebody says that, I don't know. What do you want me to say? I don't know. Okay, so with a relation, for each input there is at least an output. Now, real life example, I don't know. Well, just figure it yourself. A real life example. A real world example. You can figure it yourself. But let's look at mathematical example. Okay? Mathematical example, which is also a real world example. But you know, when I say real world example, I mean maybe something that is you can easily see or you easily witness. Okay? But let's look at, if they ask you real world example, you can give this mathematical example. So let's say this here. If we have this, let us define a function f from x to y. Okay, this means we define a function f from x to y. That is what it means. So x is the set of inputs. X is the set of inputs. Y is the set of outputs. Okay, like I said, inputs are independent variables. The values of inputs are the values of the independent variable. The output values are the values of the dependent variable. So, you know, let's have x is an element of this. Let's say that this is that x is the set, and this lowercase, the uppercase x, is the set of all inputs, the set of all independent variables. And the lowercase x is an element of this. Y is an element of this set. So the lowercase y is an element or a member of, that is a member of or a element of the set of the dependent variables. That is the uppercase y is the set of the dependent variables, or the set of all the outputs. So you see here, this is a function f defined from x to y. Alright, so first case for relation. Let's start with something that is not a relation. Okay, let's start with an example. Something that is not a relation. We'll give several examples so that you can have an idea of what I'm talking about. So now, for this first case, let's say let's define f, a function f, from the set of real numbers, real to real. So this is what I mean by real numbers, a set of real numbers, set of real numbers, two real numbers. Okay? And let's have, for this video we shall be using mapping or correspondence. Remember in the first video we talked about the ways you can represent relations, and we listed 5 ways: as a set, as a mapping or correspondence, as a rule, equation or rule, as a graph, and as a table. Okay, those ways, 5 ways of representing relations. Now, let's define this function here. Okay, x is a set of real numbers, y is a set of real numbers. As you can see here, x, y. So if we have this here, let's have, don't mind my diagram, okay? That's not too bad, is it? Okay. This is now like this. Okay. Let's draw. Let's see. Let's see here. We have this. Much better, right? Don't it? Don't it look much? It looks much better, don't it? Don't it? You know, this is speaking like from the south. If you say something in the positive, you ask the question in the negative. It tastes good, done it. It tastes good, done it. And then if you say something in the negative, you ask the question in the positive. It don't taste good, does it? Hey, you say something in the positive, you ask a question in the negative. It looks nice, don't it? Okay. Then if you say something in the negative, you ask a question in the positive. It don't look nice, does it? Okay, so this looks nice anyway. It's right. It's nice. So this is our x maps onto y. X maps to y. So let's have this here. Looks like this one is kind of bigger. But let's move on, folks. Let's move on. So if we have this x from x to y here, and let's say that f of x is let's say that f of x is square root of x. Square root of x. From real to real. Now this means positive square root of x. Positive square root of x. That is what it means. From real numbers, if we say from real to real, from reals to reals, that's from real numbers to real numbers. So if we have this now, let's have this as negative 1, 0, 1. Right? Now remember, this is the function here. Okay. Let me not call it function for now. Okay. This is the definition of the function f. We define the function from reals to reals. Okay. The x is gonna be all real numbers. The y should be all real numbers. Then the rule is square root of x. Alright, let's do this. Square root of negative 1. Square root of negative 1 is what? It's a complex number, I. Right? It's I. And remember, this is gonna be a real number. So is I a real number? No. I is a complex number. So 0, square root of 0 is 0, square root of 1 is 1. So as you can see here, 0 maps to 0, 1 maps to 1. But negative 1 does not have any output. Remember, with relations, we say for each input, there is at least one output. You cannot have any input that does not have an output. You cannot. You cannot have any independent variable that does not have a dependent variable. You cannot. But as you can see here, square root of negative 1 will give us a complex number. So because of this right here, relation is no. No. Let me use yellow. Let me use the yellow chalk to write this. So is this a relation? No. This is not a relation. No. Because you have an input that does not have an output. Okay? Function, of course, if it is not a relation, it is not a function, because like I said, all functions are relations. And if it is not a function, it is not a one-to-one function, it is not an onto function, and it is not a bijective function. So this is no for this. Does this make sense? Now remember, we say, remember this is the domain. Well, this is not even a relation, so we should not talk about domain and range, because this is not even a relation. It is not. Okay? Does that make sense? Comprender? Do you understand? Una wataraya? Una wataraya? Okay, let's look at something that is a relation. Okay, let's look at another one. Let's look at here. Let's define the function f from integer to integer. Let's define the function f from integer meaning positive and negative integers. Okay, integer includes positive integers, 0, negative integers. From integer to integer. Alright? Let's define our function there. And then the rule would be x to y, f of x is equal to f of x is equal to plus minus square root of square root of x. How about this? Plus minus square root of x. Okay. Plus minus square root of x. So I'm just giving you examples, and you can call these real world examples. You can, you can if you want to. Okay. With this one, from integer to integer, f of x is plus minus square root of x. But these are integers. Okay? These are integers. So, positive integers. We're going to talk about positive integers. Okay? Positive integers, not just integers. So, positive integers only. Positive integers. From positive integer to positive integer. Or from positive integer to, from positive integers. Yes. To integers. From positive integers to integers. from positive integers to integers. Okay, let's see what we have. So if I have here, from positive integers, only positive integers only. Okay, if I have here 1, 4, 1 and 4. Okay, 1 and 4. And I have here negative 1, 1, negative 2, negative 1, 1 and 2. So look at this here. Because positive integer meaning that only positive integers can be here. And then integers could be any of them here. Alright, so square root of 1. This is plus minus square root. Okay, so square root of 1, it could be plus 1, it could be minus 1. So this one maps to minus 1, this one maps to 1. Square root of 4, it could be minus 2, this 4 maps to minus 2, this 4 maps to 2. So folks, let's look at this. Let's look at this. I'm trying to give you several examples so that you can really grasp this concept. This concept is not difficult, trust me. So I'm trying to give you several examples so you can grasp it. Is this a relation? Now the domain is 1 and 4. The codomain, which is also the range, as you can see. Let's say here, let domain be B, let our domain be B, let our codomain be C, and let our range be R. So here, the domain is a set. The domain is a set. Here, domain is the set 1 and 4. The codomain is also the set negative 2, negative 1, negative 1, 1 and 2. Oh, this is a set, please. So use braces. Use braces because it's a set. I think I taught you how to draw this, to draw braces in part 1. Okay? I taught you how to draw it. And then the range is still negative 2, 1, negative 1, 1 and 2. Okay? The cardinality of the domain is 2. Cardinality of the codomain is 4. Cardinality of the range is 4. Cardinality of the domain is 2. Cardinality of the codomain is 4. Cardinality of the range is 4. Okay? All right. That's the number of elements in the set. So as you can see here, what is a relation? Every input has at least an output. Every input has at least an output. So like I said, one input can have one output, it can have two outputs, it can have 100 outputs. In this case, the input 1 has 2 outputs. The outputs of 1 are negative 1 and 1. Like I said, the images, the image of 1 is negative 1, the image of 1 is also 1. Image. Okay, the image of this is this. So these are the images here. The image of 4 is negative 2, and the image of 4 is 2. It's still output. Okay, the output of 4 is negative 2, the output of 4 is 2. for this here, for this rule. So, is this a relation? Yes, it is a relation, yes. It is a relation, yes. Yes. It is a relation. Is it a function? Now, we get back to what we talked about in functions. Function is a relation, that's number one. Is a relation in which for each input there is a unique output. Okay, so with a function, two people can make the same grade on a test, but one person cannot make two different grades on the same test. Have you ever seen somebody make two different grades on the same test? Have you seen that? Have you seen that? So with a function there is a unique output. Meaning that, okay, we can have two inputs with the same output, no problem. But we cannot have one input with two different outputs. We have, for relation, we don't care. Relation, an input must have at least an output. We don't care whether the input has 100 outputs. We don't care. With a relation, an input must have at least one output. With a function, an input will have a unique output. Two inputs can have the same output, but you cannot have one input having more than one output. No, with a function. So some people will say the first component will not repeat. They will say first component will not repeat because you have one -1, comma, and then 1, 1, meaning that it's repeating. When you write this as a set, you have it as 1, -1, 1, 1. You write the braces, parenthesis, 1, -1, comma, parenthesis, 1, 1, close the parenthesis, comma, parenthesis again, 4, -2, close the parenthesis, comma, and then 4, 2, and then you close it. So what I'm saying now is here. You notice. So because some of you might say, why don't you write it? Okay, well I've written it here. So go and read it. Okay, so they might say, okay, the first coordinate, which is the x, will not repeat. That is the way some textbooks define it. But I want you to understand this concept. I really want you to understand it. So that's why I'm trying to use simple examples. That makes sense, right? Does it make sense? Okay, so you cannot have an input having more than one output, no. But you can have two inputs having the same output. Two people can make the same grade on the test, but one person cannot make two different grades on the test. So is it a function? No, it is not. And if it is not a function, it is not a 1-to-1 function, it is not an onto function, and it is not a bijective function. That is with this. Okay, let me explain 1-to-1, onto, and then bijective function. So with 1-to-1 function or injective function, we say 1-to-1, which means that it is first and foremost a function. A 1-to-1 function, number one, is a function. Just like you have a function, number one is a relation. Okay? A function is a relation in which for each input there is a unique output. Now, 1-to-1 function is a function. First and foremost is a function in which for every input there is a different output. 1-to-1. Everybody stay by yourself. Okay? For each input, or for every input, for every input there is a different output. That is 1, 2, 1, 1, 2, 1. So this input have an output. This input has an output. This input has an output. Those two inputs will have the same output. That is why we call it 1, 2, 1 function. No two inputs will have the same output. No. Each input has a different output. Okay, that is a 1, 2, 1 function. Onto function. For onto function or surjective function, you have that there is every element of the codomain. X is the domain, Y is the codomain. For onto function, it is a function. It's a function, first and foremost, is a function in which every element of the codomain is at least an image of an element in the domain. Okay, like I said, with a function, two inputs can have the same output. So with the onto function, you want every element of the codomain to be at least an image. To be an image, okay, not at least an image, no. To be an image of at least an element in the domain. That is onto function. And then bijective function is when it is both 1, 2, 1 and onto. Okay, a bijective function, number one, first and foremost, is a function that is both injective function and surjective function. Okay, but we will do examples and you will understand it. Okay, don't worry. So, but do you understand this one at least? Why this is a relation, this is not a function. And if it is not a function, it is not an injective function, it is not a surjective function, it is not a bijective function. Okay? The next example, let's give the next example. So let's join this here. Join this well. The next example we shall give is, let's have from integer to integer. Okay? From integer to integer. From integer to integer. Integer to integer. It doesn't matter whether it's positive or negative. From integer to integer. So, we have this f of x, from integer to integer, f of x is equal to x squared. X squared, that's the quadratic function. Okay, that's the graph. The graph of a quadratic function is your parabola. Yeah. F of x is x squared. Okay? Let's see. So if we have here -1, 0, 1. -1 all squared, so we have 0, 1. So here, -1 all squared is 1. 0 all squared is 0. 1 squared is 1. Okay? That is your quadratic function. From integer to integer. From integer to integer. Okay? Here, let's write this. First, is it a relation? The inputs, the domain, as we see here, the domain is -1, 0, 1. The cardinality of the domain is 3. The codomain is 0, 1. The cardinality of the codomain is 2. The range is 0, 1. The cardinality of the range is 2. Okay? Every element of the codomain is part of the range, is a range, is an image of the element of the domain. So, does every input have an output? Yes. So, relation, yes. It is a relation. With a function, with a relation, two inputs, one input can have more than one output. But here, do we have any input that has more than one output? No. We do have two inputs that have the same output. Like I said, two people can make the same grade on a test. So -1, the output of -1 or the image of -1 is 1. The image of 1 is 1. So two inputs can have the same output. So is it a function? Yes, it is. C. S function. X function. C. S function. Right? Upper function. Okay. Yeah, upper function. So now, is it a 1-2-1 function? Is it an injective function? 1-2-1? No. Because we have two inputs that have the same output. The output of -1 is 1. The output of 1 is 1. For 1-2-1 functions, each input will have a different output. Each input will have a different output. So this is, no, it is not. Now, if you guys, because this is algebra, but this is also discrete math. This is also discrete mathematics for CS majors, computer science majors. And also for some math majors, you still do this in real analysis. You still do this. So, if you're a computer science major, okay, for a function is injective. Injective function. Let me write it here. Injective function, or 1-2-1. 1-2-1. Injective. Injective, if a function, this function from x to y is injective. From x to y, x to y is injective. Is injective. I hope you can see this. Is injective if and only if. If and only if you did this today. Is a biconditional statement. Biconditional statement in logic. In logic, is a biconditional statement. If and only if. Let me draw it well. If and only if Okay? For all x1, x2, for all x1, comma x2, element of x, for all x1, x2, element of x, okay? F of x1 is equal to f of x2 implies that, I'm going to write it here, for all x1, x2 element of x, f of x1 is equal to f of x2 implies that x1 is equal to x2. That is your injective function. Injective function. Okay, for discrete math folks. Now for discrete math folks, let's do surjective function or onto function. Surjective function so a function f defined from x to y is surjective. A function, and like I said, what I'm writing now is in my notes, okay? A function f from x to y is surjective if and only if for all x, actually not for x, because for all y, because this is on 2. So for all y, all y is at least an image of x. So for all y, element of the set of the outputs, okay, there is at least x that is an element of the set of inputs such that f of x is equal to y. Yeah, this is onto function. Okay, so look at this here. Let's look at this here. The elements of the codomain, elements of y, is 0 and 1, are the images of the input. And the answer is yes. 0 is an image of 0. 1 is an image of -1. 1 is an image of 1. So is this function onto? Yes, it is onto. It is surjective function. Yes, it is onto. It is bijective function? No. Because bijective function is a function that is both 1-to-1 function and onto function. Okay? Onto function. Another real world example. Everybody in this world is born from a woman. So everybody is an image of a woman. Everybody in this world. Or you can say everybody is created by God. Everyone in this world is created by God. You know, forget evolution, that's nonsense. You know, they say evolution is nonsense. You know, we studied those to pass biology. You know, we learned all those stuff to pass biology. I actually made an A in biology in a WAEC, in a SSCE. It's called SSCE then. I don't know what they call it now. Was SASI or something. But we all like all those things to just pass the class. We know that God created us. All of us. God created us. So you can say every human is created by God. So it's an image. Every human is an image of God. That is an unto function. There you go. Very good example. Every human is an image, because this is an image. 0 is an image of 0. 1 is an image of -1. 1 is an image of 1. Every human being is an image of God. There you go. Good example. Every human being is an image of God. Every human being. That's a good example for it. Okay, so does this make sense? Right? It makes sense, right? All right. Now let's do the next example. The next example, let's still have it from integers to integers. Let's have it from integers to integers. Okay? Let's look at the next example. Let us have it from integers to integers. All right. Integer to integer. If we have a linear function, so if we have f of x to be something like 2x plus 1, linear function, f of x equal to 2x plus 1. All right. So let's just use simple examples here. -1, 0, 1. 2 times -1 is -2. -2 plus 1 is -1. You owe 2, you have 1. Okay, so you owe 1. 2 times 0 is 0. 0 plus 1 is 1. 2 times 1 is 2. 2 plus 1 is 3. Right? So -1 maps to -1. 0 maps to 1. 1 maps to 3. Right? Right? So here, is it a relay? Now, here is, as you can see, the domain is -1, 0, 1. The cardinality of the domain is 3. The codomain is -1, 1, 3. The cardinality of the codomain is 3. The range is -1, 1, 3. The cardinality of the range is 3. Okay, look at this here. Is this 1, 2, 1? Is this a relation first? Let's not jump. Let's start from this scratch. So is this a relation? Yes, it is. Okay, every input has an output. So this is yes. Yes. C. Is this a function? For every input, there is a unique output. Yes. Yes. Is this a 1, 2, 1 function? 1, 2, 1 function. Is this a 1, 2, 1 function? Yes, because every input has a different output. So yes, is it an injective function? Yes. Is this an onto function? Is this an onto function? Onto function. As you see it here. Is this an onto function? Every element of the codomain is an image of an element, of at least an element in the domain. So onto function is yes. Yes. Is this a bijective function? Because it is 1, 2, 1, because it is both 1, 2, 1 and onto, it is a bijective function. Yes. Okay? Does this make sense? Does it make sense? Comprende? Okay, let's look at another example. Let's look at another example. What if we have this, okay? What if we have this? We still have this here, but I'm going to do something. I'm going to just do some things. This same example, from integer to integer. But then, let's say here, we have -1, we have 0, we have 1, we have 2, and we have 3. Now let's look at this here, folks. Let's look at this. Let's look at this example here. Now with 1, 2, 1, you can say every student has a student ID. Every student has a unique student ID. You don't have two students having the same ID, right? Identity number. So every student has a student ID number, a unique student ID number. You can also say every person has a social security number. Every person has a social security number. You don't have two people with the same social security numbers. Okay, that's just example, examples right away you can give. So look at this here. This is still okay because remember we said from integers to integers. These are still integers here. These are integers. So it's possible to have something like this. It's possible to have something because these are still integers. They are integers. So here, 2 times -1 is -2 plus 1 is -1. -1 maps to -1. 0 maps to 1. 1 maps to 3. So look at this here, folks. Look at this here. The domain is -1, 0, 1. Okay, that's fine. Cardinality of the domain is 3. The codomain is -1, 0, 1, 2, 3. Cardinality of the codomain is 5. Cardinality of the codomain is 5. The range. Now this is where you look at. You look here. The range is -1, 1, and 3. Cardinality of the range is 3. Do you see the difference between the range and the codomain? The codomain is a set of all the outputs. But the range is a set of the outputs that are images of the input. Okay? With the codomain is everybody here. Everybody here, folks. Everybody here. But with the range is just those values of the outputs that are images of the inputs. That is the range. It's a set. Does it make sense? Right? It makes sense. Okay? So codomain is everything here. But the range is actually the elements of the codomain which are images of the elements of the domain. So codomain includes range. Okay, it includes that range. Okay? Now, is this a relation? Every input has an output. Has at least an output. A relation. Every input has at least an output. Yes, it is a relation. Yes. Is this a function? Every input has at least. Every input has a unique output. Okay? With a relation, every input has at least an output. With a function, every input has a unique output. Yes, it is a function. Yes. Is this a 1-to-1 function? Every input has a different output. Yes, it is a 1-to-1 function. Yes, it is a 1-to-1 function. Okay? Remember, these are integers too, so it's okay. Now, is this an onto function? Is it an onto function? Surjective function. Surjective function means every element of the output is at least is an image of at least one element of the input. Every element of the output is an image of at least one element of the input. Every element of the codomain is an image of at least one element of the domain. Now, it is not. Because as you can see, 0 is not an image of anybody. 2 is not an image of anybody. Do you understand what I'm saying? 0 is not an image of anybody. 2 is not an image of anybody. So no, it's not. So because of this, this is not onto. And because it is 1-to-1, but it is not onto. Now, bijective means it has to be both 1-to-1 and onto. Because it is not onto, it is not bijective. No. So, I think we've covered the basic, I think we've covered the basic examples. At least with this here, it kind of gives you an idea of what your professor wants from you. If your professor asks you, to say whether the function is injective or surjective or bijective, you can, first of all, with it, why I chose mapping is because with mapping and correspondence, mapping or correspondence, that's what we call it, it's much easier to kind of look, it has a visual, you can easily visualize it than using sets, like putting it in sets. So with mapping, you can easily say it. Okay, we are going to stop here for tonight. For today, not tonight, this day. We're going to stop here for today. Please, if you have any questions, feel free to ask. And watch out for other videos on this. Thank you so much for listening to this video presentation, and you have a good day.